Problem 107, Binary Tree Level Order Traversal 2. So to solve this problem, we need to know two concepts, BFS and trees. BFS stands for Breadth First Search, and it works exactly as it sounds. So let's say I have a tree, and by the way, a tree looks something like this. And more specifically, we actually are going to need a binary tree, and I'll get to that in a bit. So I should actually say binary. And a binary tree is basically where every node has one of two or one of three outcomes. It can only have at most two children. It can have one child like this, or a child like this, or no child at all. But it can never have something like this. That won't be binary. But how BFS works is you would start at the root and then traverse each level, the nodes of each level, before going on to the nodes of the next. So at level 1, I'd go through these nodes before going to level 2 to go through these nodes in this order. And with that, we can solve the problem. So basically, we're given a binary tree, and we start at the root node, which is 3. And we're going to traverse it in a BFS style so that we can get all of the values within each level in reverse order, right? We want to go from the deepest to the lightest, if you will, in that order. So 3, 9, 20, and we're going to do 15, and we're going to do 7. So BFS will always start at the shallowest level and then traverse it to deeper levels. So basically what this means is that we have to append to a resulting array always to the 0th index, so that the deepest root, the deepest level with all the nodes in it, will always occupy the first position. And what I mean by this is, let's start with 3. We're going to traverse 3, and the only elements in level 0 is going to be 3. At level 1, it's going to be 9 and 20. At level 2, it's going to be 15 and 7. So 0, 1, 2. And we first get to this. So we're going to add 3 like so. And then we traverse level 1. And we're going to insert level 1 always at the 0th position. So that here it's going to be 9, 20. Then we go to level 2. And we always insert it at index 0 so that it's always at the front. So there it's going to be 15, 7. And that's how we get the result as you see here. And with that, we can program it up in Python. So to do this, we have to use a queue. A BFS will always use a queue because a queue has a first in, first out structure, meaning the first elements we put in are going to be the first elements we consider and extract. And to do that, we're going to use a special data structure called a deck. So from collections, import deck. A deck is a queue that can be added, that you can add elements to from both the left and right side. But for us, we're just going to add it to the left. Now what we're going to say is if root is none, then return empty list, because basically there's not a tree to even traverse, so there's no nodes obviously. Otherwise, we do have a tree to traverse, and we need a queue. So queue is going to be deck, and the result is going to be an empty list like so that we append more arrays to. And we're going to say while the queue is not empty, and actually the queue is still empty, so we have to add the root node to the queue to consider, right? Basically every node within the queue will represent a node that has not yet been visited. And while there's still nodes to be visited, that means we have not traversed the entire tree, hence the logic here. What we're going to say is for I, actually, we need to get the length of the current queue. That will tell us how many nodes there's going to be for us to put into the current level. So for I in range 0 to L, we're going to declare an array called cur level to store all the nodes at a given level. We're going to pop the current node called cur node by doing q.popleft. And we're going to add this to cur level by appending it like so. And what can we say? We have the current node extracted, so we have to consider its left and right children while we have the current node to work with. So if cur node.left, meaning the left child is not none, we're going to append that to the queue. So cur node.left. And the same goes for its right child, except that we just change the names from left to right. And with that, after we're done traversing this entire for loop, we have all the nodes at the current level. So we just append it to res, but more specifically, we insert it to the 0th index, and current level goes there. And after this while loop finishes, we have traversed the entire tree, so we can just return res to get our answer. So let's run it. And we see it does not work. Where's the error here? Type error string ret. Oh, I see. We have to append the current node's value, not the actual data structure. So let's run it. And it works, so let's submit. And that's the solution.